This is problem number 45, and it is an expected value question that is based around an exponential distribution. So we've got a machine that has a failure rate with exponential that is measured exponentially with mean 10 years, and payments that are going to be made on the failure of that machine. If the machine fails between 0 years and 1 year, we're going to pay X dollars. And if the machine fails between year 1 and year 3, we're going to pay half of X dollars. And if the machine fails after year 3, we aren't going to pay anything. And we want to know the value of X such that the total expected value is going to be $1,000. So this is the PDF of our exponential distribution. And even though we can't use the memory list property here, but we can avoid some of the crunchier aspects of the calculus if we just kind of rely on our intuition and the basic structure of the exponential distribution. So this is the PDF, and when you see a PDF like this, you should be able to very quickly convert that to the CDF. And then I am going to use decimals instead of fractions. So this is our distribution function, our cumulative distribution function for our failure rate. And let's put that on a line here. Here we have 0 years, the beginning of time. And here we have infinity years, the end of time. But we really only care about what happens at year 1, because we could fail and pay a certain amount between year 0 and year 1, and then again here at year 3, because we pay a different amount between year 1 and year 3, and then after year 3 we don't pay anything. So the probability of failure between the beginning of time and year 1 is 1 minus e to the negative 0.1, right? We just plug in the 1 right there, and that falls out quite nicely. The probability of failure between year 1 and year 3, well, let's think that through. If we failed in year 3, we would have this expression, because we just plug in the 3, and 3 times 0.1 is 0.3, or the negative 0.3. But that is the probability of failure between year 0 and year 3, and we want between year 1 and year 3, so we will just subtract off the probability of failure during year 1. So watch your negatives, but the 1s are going to cancel, and this term right here is going to become positive, and if you do enough exponential distributions, this will start to seem very, very familiar. So here's our probability of failure between year 1 and year 3. Okay, now let's just match up the payments that we would make. If we fail between the beginning of time in year 1, we pay X. If we fail between year 1 and year 3, we pay 0.5X. And if we fail after year 3, we don't pay anything, so we don't care about that at all. Let's write an equation and solve. Amount we pay times probability of failure plus amount we pay times probability of failure. And then if we convert this to decimal in our calculator, we'll get 0.9516x. Same thing here, convert this to decimal, multiply it by 0.5, and we get 0.8201x. And we set that equal, should probably set it equal up here as well, to $1,000, because we want the expected value of our total payment to only be 1,000. So the combine like terms, and we get 0.1772x is equal to 1,000. Do the division, and x is 5644. So the final answer here is D. And I hope that is a little bit more clear than what's in the calculus, than what's in the answer key. Because if you understand the structure of the exponential and how expected value works, you can make the calculus a little bit less crunchy, and the overall approach to the problem could be a little bit more intuitive.